right, this session's going to be about drone mapping, but not specifically about drone mapping, about hyperscaling a service on ARM. So you'll kind of learn that this is kind of an end use case. So who am I? Principal software engineer, work at Linaro's technology division. And you might wonder why you saw me up here doing an IoT demo and now I'm giving you a hyperscale talk. It's because we work from basically the firmware level to the cloud, so we're full stack. And then just kind of a little bit of why I chose drone mapping. So I've been piloting model aircraft since like 2004, before they were ever called drones. So I really like aviation. I'm, not a pilot or anything like that, but I like to fly RC aircraft. And so this is kind of where, my passion can intersect with my professional career. So I fly fixed-wing aircraft, quadcopters, and then long-range FPV systems, so flying out 20 miles away, autopilot systems, and I'm really into 3D printed aircraft. So that's just kind of my background of why I'm giving this session, so I can put some context to what we're going to talk about next. And at any point, if you guys have any questions or want specifics, go ahead, just throw your hand up and we can address them there. So what's a drone mapping service? So a user is going to provide aerial images, which are processed by a service that we're going to build to create a two-dimensional geolocated orthomosaic, and also a three-dimensional point cloud and textured model. And we're going to do this all with open source software. So let's just get into a demo right away so this can be interesting. So what is the end result going to look like? This is our service, Open Drone Map. And what we have today, this is actually a really terrible stitch, so I'm going to show you something different here. We flew a drone this morning and collected these images, and we processed a 1 gigabyte data set into a three-dimensional model, and so you should be able to kind of rotate it here so you can see depth. This is our hotel. So this is kind of what we're going to build, and if we go to the dashboard here, we're going to add a new project. Of course. So create a project, and we're going to upload some images for this project. And just so we can keep it within the time frame of this presentation, we're going to upload 40 aerial images. And you can kind of see here from the preview, these are top-down aerial images, and I'll go into that a little bit more. But we're going to upload them now. Hopefully this goes quickly. It's not going too bad. And then we're going to name this task. And there's a whole bunch of processing options within Open Drone Map, and I'll get into the software components. There's OpenCV, OpenGV, OpenSFM. There's a ton of image processing computer vision libraries that are needed to run this service. And it all runs on ARM64, so as we'll see here in a moment. So I just want to enable XIF. So we uploaded our 40 images to the service, and in a moment here, it'll tell me it's ready to start processing. So now it's off to the races, and what we'll see here, it's uploading the images to the processing node, and this is going to be live output of the processing node processing the images. So it's going through each image, and what it's going to actually do is resize them, because we don't want to be doing full-size images. It's going to take too long, so we've actually set it to resize the images first and then analyze them. So it's going to pull the focal lengths out of the images. It's going to pull all of the geolocation data out of from XTIF. Okay, so while that's running, we'll come back to that in a second, but I want to talk more about the service and how we built this thing. So let's go back into present mode. All right, so why don't we just map Budapest with a drone, right? And that's what that first 3D model was from. Was this morning we flew a drone, we captured 180 aerial images, and we were able to generate a 1 gigabyte data set and process them within 1 hour and 6 minutes on ARM64 servers. So what's very impressive about this is we're getting to the point now where I'm seeing almost speed parity with Xeons when it comes to processing images like this. So that's very good news for the ARM servers, or just ARM ecosystem in general. So what was our flight plan? You basically tell the drone how much image overlap that you want, and what area you want to map, and then that ring in the middle is an orbit. So when you're doing structures like our hotels and stuff, you want more depth to the photo, because it helps the photogrammetry stitch together a little bit better. So that we basically went over all those lines there, and then we did a loop around the outside to kind of get some more context for the image processing. And then on the left-hand side here, those are the points after they've been analyzed by the software to know exactly where those photos were taken in the air. if that makes sense. So that's kind of geolocating the photos. And that's what this will do, is it'll basically try to lay out the photos where they were taken and find the common points and then stitch from that. Any questions? Good. So what do the aerials look like? These are 60% overlap aerials. These were taken this morning. So we're working with a live data set. The data set we just started processing is something that I've done previously, so it'll be different than this. So let's talk a little bit about what Kubernetes is, because that's the orchestration framework we're working with. So it's commonly referred to as K8s. It was originally designed by Google, and they use it for a lot of their services. And then they donated it because they realized that if they're the only ones contributing to this project, that it's going to die over time or something else will come in and replace it. So they gave it to the Cloud Native Foundation. And really, it's just an open source platform for automating deployment, scaling, and operations of application development using containers. So it usually works with the Docker container tool, although other container runtimes are supported, and it coordinates between a wide number of nodes running Docker. So why did I choose Kubernetes? There's a few reasons. So they have load balancers for services, so you don't have to build those yourself, because those can be complex. They create a virtual IP, which other services use, so the DNS names will map to the service name. So when you do a service discovery, all you have to know is, I need a database service. It'll return service names, and then you can simply use them in your application and don't have to know, what port Postgres is running on or anything like that. You can get all that from your load balancers. And then it routes traffic to the underlying pods, so the actual containers that are running. And it allows us to deploy services and scale them out horizontally, because behind a load balancer, then the traffic can be routed through them and can be distributed between n number of pods. The other neat part is the autoscaler. So this is horizontal scale. So when I talk about horizontal scale, I mean the sheer number of nodes or pods that you run underneath the load balancer, where vertical scale is typically you throw more resources at something and you scale it up because you have more cores and more memory. So we're talking about being able to deal with more traffic when we talk about horizontal scale for the most part. There's also health checks. So we can build in our own custom health checks to make sure the services are performing properly, and they have built-in ones, and you can create your own and expose an API within your container to do health checks. There's a good storage abstraction. So you can abstract NFS storage shares, Ceph, S3, Flocker, whatever you want, but basically to the pod that's actually running, it doesn't matter. It's just another volume out, and Kubernetes deals with the actual talking to the larger storage service or the object-based storage systems. I think this is the biggest one, pod networking. So they provide different networking layers for Kubernetes with Docker. You can have different pod networks, but really you're kind of using the Docker network with this. Other people can create essentially virtual routers that you can use with different services. So Weave does L2, L3 level networking, and Calico does L3. So there's a whole bunch that you can choose from based on your networking needs. So I get this question a lot, why not use Docker Swarm? Well, Docker Swarm's a really good orchestration system in its own right, but it depends on what you care about. So like the two big things up here for Docker Swarm is multi-network per container, app networks, and distributed volume storage, right? Those things are kind of why you would use Swarm. Now on the other side, Kubernetes, there's dynamic DNS service, there's the load balancers, there's container replica failover. I mean, you get basically kind of more of the production level services that you expect running a highly scalable, highly available web service. So that's, you can go to the slides and look at this if you're curious on details, but this is kind of why I've chosen Kubernetes over Swarm. So let's talk about the big problem. So Kubernetes on ARM64. I'm not sure how many people, if many, have ever done this before. I've never met anybody that has. I'm sure there are people out there that may have played around with this. So I kind of went down the road of seeing, well, what's it going to take to get Kubernetes running on ARM64? And there's missing pieces to the puzzle. So the biggest one was there was no ARM64 container for the pod networks. And the way the pod networks work in Kubernetes is they're actually containers. So of course, everybody built their containers for the pod networks using x86 architecture. So the first thing I had to do was figure out how to rebuild the pod networks for AR64. So I've done that, and I've contributed that back to the Weave project, so you can actually pull AR64 Weave pod networks directly from Weave now. So that would need to be done with the other pod networks as well if you were interested in running them. So basically, this is the command you run now, and it'll pull in the Weave container, and bam, all of a sudden you're routing packets on ARM64. And if you're curious, the Weave net pod, and actually it's a daemon set, so it's like the DNS server, DHCP server, all of those are considered the daemon sets. They run on Alpine Linux. That's what their containers are based on. So let's talk about the cluster that I'm using. So it's 3 physical nodes, because that's all I have. There are 16 ARM64 cores, 32 gigs of system memory. There's spinning disks, upstream Tiana Core EFI with ACPI, and then we're running the enterprise reference platform, our latest one from 1612, which is the 4.9 kernel, and I'm choosing to use CentOS. And then so they didn't have any CentOS 7 packages, so I've gone ahead and packaged them and made them available. I'm actually in the process of talking with the Kubernetes team about enabling multi-arch builds for CentOS so that they can provide them through the official repo. So then I'm using Kubernetes v1.5, which is the latest released version. There's 1.6 RCs out there. If you're interested, you could probably pick up my packaging steps and pull them in. So for persistent storage, just because it's easy, I'm using NFS. You could easily use Ceph or S3, but I just wanted to keep it simple. I wouldn't recommend NFS for large-scale deployments. Obviously, NFS isn't infinitely scalable. Just don't do it if you're going to really do a production service. Use something else. So Ceph would be a good choice, in my opinion. I'm using Docker 1.13 with Overlay 2 storage driver, so I'm living on the edge. There's been some issues, but so far it's worked pretty well. And I'm using the IPv6 support in Docker with that same Docker setup. So let's talk about the stack that we're going to run here. So from the firmware and kernel level, ACPI, UEFI, reference platform kernel. Then we've got our distribution layer, which is CentOS using the enterprise reference platform. And then we've got Docker and Weave and Kubernetes on top of that. And then we're going to run Postgres, Django, Nginx on top. It's a pretty standard enterprise stack. Now, why did I choose a drone mapping application? I could have just done a simple Django web app and it would have been the same. Well, because it doesn't actually really show what the hardware's capable of, right? We want something, we're all low-level developers. If it's not being built with GCC or LLVM and it's not crushing cores, then it's really not a real service. So this open drone mapping has got all the web pieces to it, but it's also got a processing aspect, which I think is very important to look at too. So what are we going to do? How are we going to build a scalable service on Kubernetes on ARM64? Well, we have to have a load-balanced HTTP front end. So we're going to use Nginx in containers. And we're going to have one replication controller, which is going to provide a virtual IP address. So all the input traffic from users are going to go through that. Then there's going to be 3 replicas running behind it, which the load balancer is going to distribute those HTTP requests to either Nginx containers that are running. And then the pods are going to forward traffic to the backend service. And the backend service is written in Django. And so we're using GUnicorn there to support UWSGI protocol. And so we're going to have, again, one replication controller, which is going to deal with all those requests, and then hand them down to the individual containers. So I'll show you what this looks like in a moment. And here is the crux of it. I don't recommend you ever try to do this with Postgres. Don't do it. It's a bad idea. I'm telling you right now. But I'm using pgpool2 for middleware to basically broker between the client and server side of Postgres, so we can have a master replica and essentially a slave replica, and then you've got another container kind of brokering all that. If you can at all, use something that's hosted. They take all the complexity away. You just talk to the database. Everybody's happy. If you have to maintain one of these things, I'd recommend really understanding the underlying technology that this is providing. So, holy cow, what does that look like? So this is the user here. This is you guys going to a website, and you're going through a load balancer. And this load balancer is determining which pod hasn't, serviced the request last, and let's hand it off to that pod. So it's going through Nginx here. Now, if you notice, what we've got here is a content delivery network. We have to serve static assets from the back end, because typically they're generated there. So our backends, when they start, will copy their static assets out to this content delivery network, which is running on NFS, which will give them, basically, you'll do a volume mount to the Nginx pod so they can serve the latest static assets. So then the Nginx take the HTTP requests, and then they translate them to UWSGI, and they pass them on to the back end, which goes through another load balancer, and then to our back end services here. Now, these scale-out lines that I put here, this is where you scale out. So as load increases, you just add more pods behind the load balancer, and then essentially your service can deal with more traffic. That's the idea. So we can do that on the front end, we can do that on the back end, and goodness, we don't ever want to do it back here, but we can. So you've got pgpool, which is coordinating the master and slave replicas, and they're behind their own load balancers respectively. So this is just the web part. Now, the processing nodes will talk directly to the back end via a Swagger API to pick up jobs, and I'll talk about that next. So they do the real work. They thrash machines. They bring Xeon cores to the ground. I mean, this is some heavy lifting when we're processing all of this imagery. So they pull images, they inspect it, they compile, they stitch, and then they output the final product. They do all of the real work. They're not stateless, though. So the big thing, if you're going to build a service on Kubernetes, these are containers that don't really save their state. So if they die and you try to restart them, they don't know their state. It doesn't scale that way. So this is the part that you need to design something to orchestrate that. So essentially something that measures load, and then we'll bring on more processing nodes and things like that. So this is the part that doesn't scale in the same way that the web front end does. But the good news is we can start a container and they can self-register. So it's essentially all it is finding an open node, starting a container, and then that adds more processing power to your web service. So yeah, Kubernetes is straightforward to create a highly scalable service for the most part, especially with the Django web application. But again, like I said, we're really interested in doing some serious computation, and I think that's where we're starting to see the ARM64 servers shine a little bit. So again, this project, all the developers on it have massively, huge Xeon clusters that they run all this stuff on. And so when I came to work on the project, they kind of were laughing, thinking I was running this on a Raspberry Pi 2. And we've kind of compared computation times, and we're about 15 minutes slower on the same data set. So we're getting there. It's looking really good. So let's talk about the image processing components. This is a big project. There's a lot of things that need to run on ARM64 that weren't running. So this is just the big list of all of the computer vision libraries and image processing libraries that are used. So there's a whole bunch. They really work the system well. It's a good test to see how much of ARM64 is at parity essentially with packages and software versions with x86, and we've done a pretty good job so far. Any questions about this so far? Okay, so good news. I ported anything that wasn't working to run Open Drone Map on ARM processors, and I'm upstreaming them to those various projects that you saw there. I think about 70% of them have been merged already, so we're 30% left. And when this is all done, by the end of March, we're hoping it's going to land. ARM support will land in 0.3 release of Open Drone Map. Now, why is that important, and why is this exciting? To me personally, being flying aircraft since 2004, ARM cores have been in aircraft pretty much from the beginning with flight controllers and IMUs and such. I think in 5 years, we're going to see drones that are so powerful that they can process imagery on board, right? So being able to have this running in a container on board as you're collecting images, when the drone lands, all of your stitching's been done, is huge, right? I mean, how cool is that? So we're not there yet, but I can see that we'll be there maybe in 5 years. So that's why I was very interested in doing this. Plus, I had the hardware. I felt like it was my duty to make sure cool stuff like this works on ARM. Okay. So let's just, before we start going into how to update this thing, let's just take a peek here. Okay, so is that only 15 minutes? I don't know if I'm going to be able to go the whole hour here, guys. Okay, so we got about 5 minutes left on this processing. We can kind of check in and see. Yeah, so it's generating the Google Map tiles, because you'll be able to actually see your 2D orthomosaic geolocated on top of Google Maps, so you can kind of see your resolution that was captured by your drone, overlaid on Google Maps, which is neat. So while that's processing, why don't we update it? So why don't we update our web front-end containers, right? And can we do this with one command? Yes, you can. So it's actually the wrong. So we were running latest, which was essentially, actually, let's go like this. Oops. Okay, just so you can see, we're actually running this on ARM64. And let's just see if we're loading up. You can see the Google Map tiles generation is actually running right here with 16 cores. This one's only doing single-threaded work at the moment. So let's take a look at our cluster. Okay, so these are the pods that are running, right? This is the actual containers that are running. Now, if we say, here's our services, Nginx, PG Pool, WebODM, which is the back end. We've got our database services. So that's kind of what everything looks like at this point. Now, there's 3 nodes, so these services are spread across those 3 nodes based on the Kubernetes scheduler. So let's say we want to update our Nginx pods, and essentially all it is, I'll show you, is this bit here. So we're going to set a new image, so container name. It's the same container name, but a new tag, right? So we've updated Nginx, maybe we moved up a version, maybe we've added some different optimizations or flags or extensions, right? All you have to do is put a new tag in, and we can roll an update to it. So we don't want to do latest, because I believe that's what's running now. So there's a tag called update. Okay, so now it essentially went and tried to. Okay, so what it did there, oops, PyCharm, thank you very much. Okay, so how does this update work? How did I just update a web service in real time without any downtime? So let's just go check and make sure it's actually still up. Hey, it still works, great. Now we just slid in a new version of Nginx in there and didn't have any downtime. So let's take a look at the console output. So Rollout 2 of 3 new replicas have been updated. So what it does is, since it's behind a load balancer, it can take down a container, right? Now we still have 2 instances taking HTTP traffic. It brings up the new instance. So now we have 1 new instance and 2 old, and then it takes them down one at a time and replaces them. So you never actually have any HTTP requests that are dropped, and then you can kind of slowly roll in your service and then roll out your old service. And so that's actually what it did. So now all of the Nginx pods that are running the new version of Nginx. So I can actually go the other way now, oops, and go back to the version that I was running. And we can watch it roll back. And while it's rolling back, we're still serving web traffic. So we can do the same thing on the back end as well. Is there any questions on that? Is this useful information? Yeah? Okay. So that's how you update a service, and that's, I think, one of the key pieces of Kubernetes, and they offer an API, right? Let me go back into present mode here real quick. It offers an API, so you can do this, and you can automate your rollouts, and you can change your different services, and you can do it without any service disruption, and that's kind of a big thing. So how do you scale up a service? Well, there's a couple different ways. Now, I don't have enough nodes to do autoscaler, but if you ever use like Google Compute Engine, essentially you can tell it, there are different metrics that you look for. So for like Nginx, it might be the number of requests that are processed. You can have a threshold, which then will start to scale out the nodes, and then what that means is that you also need to add real hardware to your cluster. So you scale your cluster out first, and then you scale out your services. So you can do all of that inside of Google Compute Engine. However, when you're running a bare metal cluster, unfortunately, that's not something that you can do because it's real hardware and you have to control it, and Google's got it all automated. It's pretty neat. So let's just see where we are with this. We're getting really close. Let's see if it's zipping it. Because I want to show you guys a good. Okay, so we'll just talk here for a little bit until this is done. Yeah, go ahead, David. Yep. Yes, so that's a good point. So the question was, I run Docker container locally, it's simple for me to use, what's the overhead of running Kubernetes essentially, and what do you have to learn? So let's take a look at that, that's a good question. So for our deployments here, I've got a couple different things. So at the end of this, I'm gonna tear the service down and I'll redeploy it in a minute, so you can kind of see how this all works. But let's take a look at the backend pod, actually. So this is the, here, let me move this down a little bit so you guys can see. Can you guys see that okay? Or should I make it bigger? ASAC, what do you think? Make it bigger? Okay. Okay, so this is the, oops. Nope, no thank you. Okay, so this is the definition of a service in Kubernetes. And what probably, makes sense to you is this image name, right? It's a Docker Hub image name with colon and a tag, right? But all the other stuff is foreign, right? I mean, this is all Kubernetes language on top of it. So you can do JSON or YAML format. I find YAML's nicer because I can do things like comment up my debug commands and then switch them easily and then reapply them. So essentially what this says is, okay, this is my namespace, and that's an interesting thing to talk about. So another awesome thing about Kubernetes is You can create namespaces within Kubernetes, and any pod running in that namespace can resolve the DNS names of any of your other pods. But they can't, you can set different ways, but by default, they're isolated in their own instance. So you can have like, customer one, and they have all their services running there. You have customer two in another instance, another namespace, and they're isolated. But you can also have them jump networks if you allow that. So it depends on what you're using them for, but it gives you nice like microservice isolation. So I've got my namespace, I've named my app, I told it what container to pull, and this command block right here is like your command block in Docker, right? You can tell it to override the command that's actually in the Docker file, so you can do different things. And then your ports here, your container ports. So I say I want you to open port 8000 for me because this is GUnicorn, that's what it's serving on. Cluster first, node selector, I can make it even run on a specific node if I want to. And then provide standard in and TTY. And then the restart policy is if this node goes offline and the container dies, is to always restart it. So you can define these things like that. So let's take a look at the deployment script. Because I think this shows, so basically all this stuff here is delete what's already running. If you're going to redeploy the service, I don't want that stuff hanging around. Then you create, this is the next line here, let me highlight it. You create the service based on the YAML file, right? But that's not good enough. Actually, excuse me, that's the deployment. The deployment is different than the service. The service is here, and what this tells the service to do is expose port 8000 of that backend to the load balancer. So when you make requests on port 8000 against the load balancer, that's where it knows to get that port number. Now down here, you can see I remapped it, right? So this is the web front end that I'm using. So I say the target port, the Nginx is serving on port 80, but I want you to actually serve on port 8080, and I want you to map it to an external IP address. So this is how you basically port forward your services outside of Kubernetes network. And then I have a port forward on my router. If you notice, we're at 8081 here. That's actually being translated from the external IP of a Kubernetes node from 8081 to 80, and then giving it right into Nginx. So all that traffic is going there. So you've got things like that. So this is all different than what Docker provides. It's more complex. There's a whole bunch of stuff that you can do. They actually have a good documentation for it, but it's extensive. So you can find yourself lost in it very easily. That's the downside of Kubernetes, unfortunately. I will say, so since version 1.4, they've made it incredibly easy to set up Kubernetes. Before, let me see if I can just pull it up, because it's ridiculous. No, I don't have a link to the old one. But essentially, it was about 3 pages of how to set up Kubernetes and how to talk to the pod networks and connect them. And now there's literally 4 steps. There's 1 of 4. So you get kubeadm, which is packaged now for ARM64 within CentOS's context. I believe Debian already has it packaged upstream, so you can do this on a Debian machine right out of the box, which is nice. Then you basically install Docker if you don't already have it installed. And then you initialize your master, which is like a single command now. You just call init, that's your master. And what that will do is actually dump you out a token. So you can kind of see here, well, this doesn't really show it, but this is the join. So it'll give you a token at the end of that init command, and then you can just go to different nodes after you've installed Docker and kubeadm on them and just join them to your cluster. So it's very quick to actually join nodes to your cluster now than it was before. Let's see if this is done yet. Oh, good, it's done. Okay, so let's take a look at what this looks like. So this is the point cloud, right? This isn't going to look very good because these are just like pixels in space that it's located, right? And so this is kind of blah, but this shows you that there's some terrain here and it's stitched together. So what we actually want to see is taking that point cloud and overlaying a texture on top of it. That's where it's interesting. That's where you get a real 3D map that looks like a photo. And a lot of times, what I know I have a quarry example here, and the reason is because quarries, so gravel quarries in the United States, and I'm sure all around the world, have a problem. And the problem is, I've got all this gravel. How do I tell a customer that wants gravel from me how much I have? Because these guys are just like have huge machinery and they're moving stuff around. There's gigantic piles. So what they used to do, and maybe a lot of them still do, is they have surveyors come out and do depth surveys throughout the entire pile, right? And then they can calculate the the volume of a pile and then estimate how much gravel they have. Well, they've realized that we can fly drones, and we can fly their entire quarry in like 12 minutes and generate these 3D models, which then we can highlight the piles and calculate the volume within a reasonable amount of tolerance. So if we zoom in on this here, you can kind of see. So this is one of the piles here. Kind of move it to the side. And it's enough for you to know you could do a volume calculation on that. We could isolate this piece right here, and I mean, you can see, you basically, well, can't really tell from this angle, but this is underneath the image. You could figure out how much volume that is based on a couple of things. So that's what these guys do. They use drones now to measure it. And why does that make their bottom end better? Because they can do it every day or every week, and they know exactly how much raw material they have, whereas before they would do it once a year, and their books would be off. So now they can kind of coordinate that a little bit better. So that is this. Now, there's one less trick I've got up my sleeve. So scale up a service. We didn't talk about that. Now, if you look, when I did this command here, there it is. Okay, somebody should have called me out on this. This backend's only running one replica. I said there was 3, right? So I lied to you, sorry. But we actually need to scale this up now. So how do I scale it up? How do I say, okay, instead of one instance of a backend, I need 3. And will it still work? Will the service still work? Well, what we do is we go into the definition file that I was showing you earlier. And up here at the top, there's replicas. And I've got it set at 1 now. So let's set it to 3. And now we just do a nifty command here. It's the apply command. So anything you change on disk, that YAML file, and you want to apply it to a running cluster, all you have to do is reference the newly edited file. So we say, okay, go do it. And we look. And now we see that the containers are being created for the 2 new backend services behind the load balancer. So it doesn't matter if, basically the load balancer will not route traffic to these things until they're running. So you can essentially guarantee you're not going to disrupt your service until the container starts running. Now that's the caveat. I know I've seen people on the internet when they make containers, they'll put a whole bunch of stuff in the start script, so that basically the command where it's got to pull files and do a bunch of computation before it actually starts running. The problem with that is that delay in time, right? Your load balancer could be sending you traffic and your service isn't running, so you get a disruption. So it's very, very critical that you design your containers when they start running, they are actually running, and there's no special magic that you have to do ahead of time. That'll make the service much, much more robust. Okay, so those, now you can kind of see here, we've got 3 instances of the backend now, and we've got our updated Nginx containers, and we still have all of our replicas, and you can kind of see here how many times they've been restarted. So like if I lose a node, then what Kubernetes will do is, okay, restart those nodes on a new node over here. So they're all behind the load balancer, so really you shouldn't actually see any service disruption. Let's see if our backend still works. There we go. So that is all I have. I know I think I'm a little short on time here. So thank you for coming. I hope that was somewhat interesting. I tried to, bring in some other technology rather than just all software and have a talk about this because I think it makes it more interesting and more relevant to what we're doing. Is there any questions? Go ahead. Go ahead. Okay. Yep. Sure. Yeah, so the question was, why run on ARM? What advantage do we get from that? And then the second part of the question is it energy efficient? Is it resource efficient to process the images on the drone? Well, I would say it's interesting to run on ARM because most of the drone equipment already runs ARM cores. Now there's Intel-based drones, there's other architectures that run IMU software, but for the most part, it's like the mobile industry. Most of it runs on ARM. So that's why I thought it was interesting to run. Now, you can't run this stuff yet on a Raspberry Pi. There's too much memory usage, right? I mean, you need an ARM platform that has at least 8 gigs of memory. But I think that's coming, right? I think we're going to see handsets in the next 2 years shipping with 8 gigs of memory. That's the whole reason we moved to 64-bit, so we can address more memory, right? The second part is it resource efficient to run the processing on a drone? Now, with like DJI's Phantom 4, right? They're doing, so the way Follow Me used to work, let me step back a little bit, on drones was that you had a GPS beacon that would talk to the drone, and you'd walk around with it, and the drone would follow your GPS beacon. And then DJI came out with a computer vision system that runs on board to actually select an object in space, make a 3D model of it, and follow it around. It's called Active Track that you may have seen. So they end up saying, well, it's actually better to do the processing on board, and that it makes the drone experience better. Now, when you're doing jobs where you're mapping quarries for customers, if you have to go take your images off-site, and sometimes these quarries are quite remote, you have no internet connection at all to process the imagery, so you could do the volumetric calculation of their piles for you. You have to drive away, you have to upload the images to something that's bigger, a bigger server to do these computations, and then get the output files and then send them out to your customers. So I would argue that being able to, when the drone lands or shortly after the drone landing, if you have all the imagery that you can share directly with the customer when it lands, that's an advantage. And that's why you would use ARM. The other thing is just having talked with some of the quarry owners, that's advantageous to them because they can, they get a phone call from their customer saying, I need to do 40 tons of asphalt, I need this much gravel. They have to wait for the drone operator to go back, process the images somewhere else, and call them back and saying, this is how much gravel you have. If he can know when that drone lands after 15, 20 minutes, like you just saw there, of what the pile is, then he could call that customer back and get that sale. So it's a competitive advantage almost if you can do that. Now, is it efficient? Probably not. It's going to use more battery power, right? And batteries are, I think, where drones and really the rest of the industry needs to improve. I mean, I think Tesla's making a heavy investment in the battery technology. So I'm hoping over time that becomes less of an issue. But that is where it is inefficient, is it's going to go through your battery faster. But the good news is most of these drones now can fly for 30 minutes. So if you're talking about mapping something that takes 12 to 15 minutes, it might use your entire battery to do that. But in the end, you can get your customer that data faster. So that's kind of been my reasoning. I did also work on the enterprise reference platform, so that was kind of why I was like, hey, we're starting to see hardware now that's actually really good and fast, and it actually does use less power than Xeons, and it's not that much slower. So that's kind of why the geospatial engineers that actually work on this project, and I've been talking with them, are excited about it because now there's another competitor in the market that that flies around natively, that processor flies in their drones that they use today, and that they can kind of see the future. So it's nothing that's going to probably be used today, but maybe 5 years from now, it's something that's an interesting technology. Any other questions? You could. Okay, good question. So everywhere in that code is, SSE instruction sets by default. Right, that's been the biggest bane of porting this stuff, is that just, getting it compiling right with the right instruction set, no one really, when they were building those projects, had thought about maybe other architectures want to build this, so that's been a pain. Pointer size and things like that, that's been a little bit of an issue, but not too bad. I mean, there's only 2 projects that need to be fixed up, in regards to that, and most of it was build stuff, and it just worked. It was really nice being able to use, so I think most of the containers are built on Debian Jessie, and just being able to enable backports to get some of the newer software versions that they required in there was like really helpful. So, I mean, a lot of this was standing on, the people that work on Debian really, that they had done a lot of work on ARM64, and so it kind of proves that, we're getting closer to x86 as far as package parity goes.
No issues with muscle?
What's that?
You said using Alpine, which uses muscle instead of POC.
That's correct, yeah.
No issues?
No, that was Weave, right? I mean, I was surprised. I actually thought I was going to run into that, right? But it didn't end up happening, and it works great. Yeah.
Any memory uploading issue, or your software is highly redundant using like different libraries and all that?
So not when building the software, no. But I do have an issue to sort out. I can actually probably show you. Since we have a little time, let's show you. I've got another issue, essentially where I think there's some amount of memory corruption that's happening, and so I didn't show you the 2D orthomosaics being overlaid on Google Maps because that's actually broken on ARM at the moment. And it's essentially spitting out the the hex character is unrecognized, so it's getting an odd non-hex character in the buffer, and it's complaining about it, and it's actually crashing. So let's, I'll show you guys how to introspect these containers, because I think that's kind of interesting. Let me close all this down. 1 second. So let's get our pods, and let's connect to one of the backend instances. So Docker has this whole idea too of basically tailing the logs coming from the container, which is super helpful. Because I have 3 backend instances, I actually need to monitor all 3 of them, because when the crash happens, the load balancer is going to hand the request off to the right backend, or the backend that it chooses, so we have to have both open, or actually all 3 open to actually see the error. And let's choose the other backend. Sorry, I'm doing some SSH tunneling here. Let's get the last one. Okay. So that's all of them here. So if we go and we open up a map of this, bang. That's where it usually happens. Yeah, so this one down here was the one that actually intercepted that request from the load balancer, and yet we have an invalid hex character. So there's a backtrace here, and I have a feeling it's due to memory corruption. It's actually using uses the Postgres, PostGIS extension for Postgres for the geospatial information, and what's being handed down from the back end, I think, is corrupted characters that it's getting out of memory. So that's one issue that is still pending that I need to sort out. But yeah, I do suspect that there is some potentially memory ordering issues or even memory corruption that's happening on ARM that needs to be sorted out. Just so you guys can see, well, you can kind of see this here. I look, maybe some of you guys are actually on this website right now and looking at it, because this is a live URL. But if you go to like processing nodes and you click around here a little bit, you can actually see that the different web requests are getting routed to the different backends. And so if we do a few more here, go look at the administration backend, maybe go here, and back to our dashboard once that loads. And we look at that again. You can see that it's spreading it around, the load balancer is spreading those requests back and forth to the different backends. And the same goes with the front end. The front end load balancer is doing the same thing with Nginx. And the same kind of thing is happening with kind of beneath PG Pool, as PG Pool is asking for the master and replica data sets and making queries on it. So, yeah. Yep. Yes. So, I've got a graphic for you here. So, there's some things that Swarm has that Kubernetes doesn't, right? I look at the dynamic DNS service being huge, right? So it uses kind of like a Sky DNS container placement management system and the load balancers. You don't get that from Docker Swarm. And building a scalable web service, if you have to build the load balancers yourself, you can do it. It's well known, but that's just something extra that you have to do. You get it for free in Kubernetes. Authentication providers, ACL management. But if you care about having multi-network per container, you need to use Swarm. If you care about using IPv6 inside your containers, you need to use Swarm, right? Because actually, this isn't listed on here, but Kubernetes doesn't support containers with IPv6. So that's something that I've asked them for, because I'm generally interested in the Internet of Things, talking to the cloud, and if you're talking about 6 billion devices, right, we're going to run out of IPv4 namespacing very quickly, and it's just not going to work. So the cloud needs to natively talk IPv6, and that's where I see Kubernetes lacking at the moment. And essentially, what the Kubernetes team has said is if you have a bare metal cluster like this is, and you get IPv6 support working, we'll take the patches. But the problem is no cloud supporter, cloud service at the moment supports IPv6 natively. So they're kind of uninterested until somebody has an offering. So I think the work will be on us to get that working on a bare metal cluster, and then once the big companies decide that it's time to stop ignoring IPv6, then they'll have something to work with. So, yeah. No, we have shortcomings. Pod networks. What's that? Okay, so the question was, with context, or with respect to Kubernetes and running on ARM versus maybe running on the x86 architecture, are we at parity? And the answer is no. So we can install Kubernetes, and we have one pod network to choose from, which is Weave, because I used Weave on x86 when I was setting up bare metal cluster. It seemed to work well. But there, if you go here, actually, you can see all the ones they offer. And to my knowledge, hang on a second. Yeah, there's the add-on page here. So all of these things here work on Kubernetes. They offer different things. There's different advantages. There's different use cases that they fulfill. And WeaveNet's the only one that works on ARM64, and I'm pretty sure anybody else has been crazy enough to try them on ARM, just because they probably don't have the hardware, right, that could run Kubernetes and do a good job. But we're getting there. I think we're getting closer to having something that's very compelling. So I would say pod networking is where we're lacking. Everything else is pretty much on par. But this is a big part of why you choose Kubernetes, is because you have all of these different options. Mm-hmm. Alex.
You mentioned earlier that when you're importing the image libraries, there was a bunch of stuff that was streamed
Yeah. Yeah, I did actually. In fact, I had to, they removed GCC intrinsics and just hard-coded everything, right, which I basically backed out. A lot of the stuff uses CMake. I don't know if you use CMake much, but it's got its own way of detecting architectures, which I don't think is very clean. So I end up, it's like this massive list of like, is this AMD 64 or i386? It's like this huge list of basically, am I running on x86? If I'm not, then, don't use SSE2, right? Those kind of things. So yeah, some projects I did use the C intrinsics. On other projects like CMake and stuff, it was just using their architecture detection and then to use the right flags from there. No. But once you get these things working, it was fairly smooth. It worked just like it worked on x86 as far as from a Kubernetes standpoint, which I was really happy to see. I'm glad I didn't find that something nasty happened. The interesting part though. WeaveNet uses IPv6 to talk between containers. So if you've got a broken IPv6 on your platform and you know about it, it's not going to work. I won't name any names, but there are platforms out there that are ARM64 that do not work properly with IPv6, and I can't run WeaveNet on them. So that's kind of why I had to have the cluster that I did instead of running, a whole bunch of different vendors' ARM64 servers in there, because there was some broken IPv6 support. Essentially what was happening is, I don't know how this is happening, but we have duplicate IPv6 addresses happening. And I have a feeling it's to do with duplicate MAC addresses, but that's just my hunch. So, any other questions?
Is there any effort to do performance benchmarking?
We do not do performance benchmarking here at Linaro with our member platforms, but it's all open source. If you've got a platform and you want to see how it performs, I've done my own research. I don't want to present it as I don't think it's fair to anybody to see, but there's power savings running on ARM64 over Xeon, especially when you run the same workload. That's why I like this project so much. I can take the same data set, push it onto my Xeon servers using the same Kubernetes setup, the same containers, right? Obviously built for different architectures, and have an apples-to-apples comparison of the workload. And I have basically current kilowatt-hour monitors on either server, and I can tell, how much power saving it is, and then basically have a power savings to time trade-off and kind of just understand where that is. But I will say it's looking really good for ARM64 right now. We're not beating the incumbent architecture at this point, but we're doing a lot better than we were maybe 2 years ago. Wookie. Yeah, I don't want to divulge. I mean, I'm kind of shielding what hardware I'm using and stuff, but just from my personal, don't take this at, this is nothing professional here as far as, it's not very scientific, but the ARM servers themselves have a higher idle current pull than the x86 servers do. That could be due to, somebody just said, we're going to turn the fans on to 100% in this rig and let them run. And that's why it's eating up all the power. It's not necessarily the CPU needing that much power. However, when the workload starts, it's a fraction of the current consumption of x86 when the same workload's running. So it's kind of a weird conclusion to come with, is that ARM64 servers at idle are using more power, but when they're under load, use far less. I mean, we're talking amps less power than their x86 Xeon servers that I've used. So, and you're talking about a 15-minute difference on a data set. What's that? Yeah, so the same data set running on ARM64 versus Xeon is 15 minutes slower running on ARM64. Yeah, total time. Sorry, I can't hear you. No, that's 15 minutes. Okay, so you want context. So on an hour, so say it takes an hour on ARM64 and takes 45 minutes on Xeon. Okay. I just don't want to get, I don't want to say, it's this much better, and somebody wrote an article and it's, could be misleading depending on the hardware. So I don't want to go down that road, but that gives you a basic idea of, so it's not bad. I mean, I can wait 15 extra minutes and save some power. So I think that's pretty exciting, and we should all be kind of excited about that. Any other questions? Thank you.